Welcome back, folks. We're going to do another Norton application of Norton's theorem on a problem that we've seen before, but we're just looking at it a little differently this time since we're going to build a different equivalent circuit using Norton's theorem instead of Thevenin's. So let's get at it. And there it is. Okay, so the first thing we're going to do is get my pen working, is find I Norton. Okay, and I Norton is I short circuit. So we're going to short circuit where the load would be and find the current there. Okay. I1, I2. And let's see, no current supplies. So we're going to go up 12, down 4 I1, down 2IX, down 6 I1 minus I2. So we're writing a KVL for I1. Okay, KVL for I1. All right, IX is a problem. We got to get rid of it. So let's write an expression for it in terms of the unknowns. And it looks like it's I1 minus I2. We can plug that in and do some distribution. Negative 2I1 plus 2I2 minus 6I1 plus 6I2, and that's equal to 0. Okay, grouping like terms. Let's see, we got I1, I1, and I1. So it looks like it's negative 12I1 and plus 8I2. And we bring the 12 over, so that's negative 12. Okay, there's our first equation as we try to find I short circuit. All right, looking at I2, ooh, we can use a shortcut on that one. Since I can use the shortcut, let me squeeze it in up here. I2, and we have, let's see, what does I2 share with I1? It shares the 6. What does I2 touch? It touches 9, and there are no sources, so that was nice and easy for us. Okay, two equations, two unknowns. All we got to do is solve it. Grab your calculator, sing along if you know this tune, and we've got negative 12, 8, and negative 12, negative 6, 9, and 0, and we get 1.8. We get I1 equal to 1.8 amps and I2 equal to 1.2 amps. Is that behind my head? It's behind my head. Let me duck. Let me duck. Ooh, there it is. Okay. I short circuit. I1 doesn't touch it. I2 does and goes in the same direction. So I short circuit is 1.2 amps, and since I Norton is I short circuit, I Norton is 1.2 amps. Okay, still behind my head, always getting in the way. It's just what I do. Let's try that. Okay, now in order to find, let's write that down. Let's even try to write it this way. Find R Norton. We've got to revert to the methods that we've been using to find R Thevenin. So there's a dependent supply in here already. So we're stuck with method 2 or method 3. For this circuit, I think I did method 2. Pretty sure I did method 2 when we were doing Thevenin on it. So why don't I do method 3? Just to switch it up a little bit and give you something a little different. Right? So we remove the load if it's drawn. So I got rid of that. I just copied it from above. So that's where the load would connect. And replace the other independent supplies. That voltage supply is the only independent supply with their ideal resistances. So it's going to be a short in this case, And then I pick out V new. Do I still have my calculator emulator up? Right, so I put V new in here, and we find I new. We'll see if there's any shenanigans on this one. Still there? Yep. Power's turned off. Let's get a value for... I mean, it could be random, right? I got two 10s in a row. Okay, that feels better. That feels like it changed, right? But two 10s in a row, that can be random. We'll go with 2. I keep hitting a random number until I get the one I want. Seems really random, doesn't it? Anyhow, so we pick out some value. Doesn't matter what it is. We pick out a value for V new, and then we go do the analysis again. And once again, I'm trying to be real careful in how I do this analysis. So don't reuse any of it. I got rid of a voltage supply. I added another one. As far as analysis is concerned, it's a whole different circuit. So you really got to be careful with it. Okay, so no current supplies. So we're writing 2 KVLs. And we've got a KVL for I1. We're going to drop across the 4 I1. We're going to drop across 2IX. And we're going to drop across 6 I1 minus I2. Back to where we started. So that's equal to 0. We got to get rid of IX again. IX is I1 minus I2. Even if it is the same as the thing above, go through the steps. Don't screw up. Don't make silly mistakes that get your grade reduced or crash a plane or something in between those two, right? Put that in perspective when you get your grades. Okay, what we're really trying to do is make you good engineers. Okay, so I did the substitution, I did some distribution of the coefficients. I just got to pull some things together here. So we've got negative 12 in front of I1, looking at these 3 I1 terms, and plus 8 I2, looking at these I2 terms. There are no sources because it got taken out. Okay, so there, the equation's a little different, but we just want to make sure we slow down, do it right. Okay. KVL for I2. We're going to drop across the 6, I2 minus I1. Oh, we can do the shortcut on this one. Let's do a shortcut on this one. Less algebra I need to do, the better, right? What does I2 share with I1? Negative 6. I1, what does I2 touch? It touches a total of 9 ohms. I2, and on the right-hand side, we're going to be dropping 2 volts. Okay, grab your calculators. This is behind my head. Again, let's get it up a little further. I1 and I2. We need a solution. So here's your system of equations. Put it in matrix form. Hopefully you're comfortable doing that by now. Negative 12, 8, and 0. Negative 6, 9, and negative 2. All right. That's what you get when you get a random number. Negative 266.7 milliamps, negative 400 milliamps. Okay, save those for later, because ultimately what we're after is I knew, and I knew, not too bad, right? I knew is I1 doesn't touch it, I2 touches it and goes in the opposite direction. So I knew is negative I2, so I knew is 400 milliamps. All that's left to do is calculate R Norton. And since R Norton is the same as R Thevenin, we can say that R Norton is V new over I new, or 2 volts over 400 milliamps. also known as 5 ohms. Okay? So if I wanted to draw the equivalent circuit, this is a Norton equivalent, we would have a current supply with a parallel resistance. That parallel resistance, since I have it right here, is 5 ohms, and that's our Norton. What do we get for a current? I Norton is 1.2 amps. Okay. All right. And go ahead and hook up a load. I'm not going to do it now. I think we've done it enough. I wanted you to see finding a Norton equivalent circuit from end to end and then drawing it. Okay. But your load would attach here. Attach load here. All right. So not that different from Thevenin's, just a little bit different look to the approach and how we draw it. Okay. So now that you know both types of equivalent circuits, it's good stuff. I want to take the brief detour to talk about I've been promising you for like 3-4 videos now, maximum power transfer, and then after that we'll talk about something called source conversions. So we're going to flip back and forth between Thevenin's and Norton's. That's what's coming next. Stay tuned and good luck.